Okay, so the next example we want to consider, let's say show that the sum of two rational numbers is a rational number. Okay, so what is the assumption here? And what is the conclusion? So here, see, this statement is not written of the form if P then Q. It says show that the sum of two rational numbers is a rational number. So, but we still can write it in that form if we want to. We are saying that if we have two rational numbers, then the sum of those two rational numbers is a rational number, right? So the only assumption here is that I have two rational numbers, and my goal is that I want to show that the sum is also a rational number. So again, because I want to show that the statement is true here, I have to prove in general, not with examples. I remember I gave this question in pre-calculus class, and many people say, okay, 5 is a rational number, 7 is a rational number, 5 plus 7 is 12 is also a rational number. So they think this is a correct proof, but this proof is completely wrong and won't get any point in the exam. So the proof has to be in general. How can I prove in general? We said if you want to write a proof in general, you can always start your proof by saying that let's say let, for example, R and S be two rational numbers. Be two rational numbers. Okay. All right, so I consider two arbitrary rational numbers. I call them R and S. They could be anything. I'm not giving any examples. And then remember we said we have to apply the definition, right? Always when we want to prove a statement. For previous examples, we said, for example, odd, definition of odd number means 2k plus 1 and so on. Now here I have two rational numbers. What is the definition of a rational number? Do you remember from pre-calculus class? So then R can be written, let's say, of the form M1 over N1, let's say, and S equals M2 over N2 for some integers M1, N1, and M2, N2. And N1 not equal to 0, and N2 also not equal to 0. So this is by definition of rational numbers. Definition of rational numbers. Any rational number can be written of the form M over N, where M and N are integers, and the denominator is non-zero. Okay, so I start with the assumption. I just have two arbitrary rational numbers. Then I apply the definition of rational number. I wrote R and S in this form. And then what should I do at the end? At the end, I want what? I have to look at the question. At the end, I want to show that the sum of these two rational numbers is also rational. So I have to add these two rational numbers in order to make sure that the sum of these two rational numbers will be appeared in my proof. So let's add these two numbers. So then R plus S will be equal to M1 over N1 plus M2 over N2. And then this is going to be M1 N2 plus M2 N1 divided by N1 N2. which also belongs to the set of rational numbers, because m1 and m1 and 2 plus m2 and 1 and n1 and 2 are integers, right? How can I show that a number is a rational number? I just need to check whether it's of the form m over n for some integers m and n. Well, here r plus s is of the form m over n with m and n integers and denominator not zero. Why? Because the numerator is m1 and 2 plus m2 and 1, which is an integer. Why is an integer? Because each m1, m2, n1, and 2 are integers, right? Product of two integers is integer. Sum of two integers is an integer. So m1 and 2 plus m2 and 1 is integer, n1 and 2 is integer. And n1 and 2, the denominator is also not zero. Why is the denominator not zero? Well, because I was assuming that n1 and n2, each one are non-zero, right? So if I have two non-zero numbers, the product of those two non-zero numbers will be also non-zero. So that's it. So we showed the sum of R in Q and S in Q belongs to, what did you say, is a rational number as desired. Okay, let's look at another example. True or false? Justify the product of two irrational numbers is an irrational number. So what do you think about this? Do you think it's true or false? Again, you know about this, right? That if you want to show it's true, you have to prove in general, not with examples. If you want to show it's false, you can provide only one example called counter example, which satisfies the assumption, but not the conclusion. What is the assumption here? The assumption is that I have two irrational numbers, and the conclusion is the product of those two irrational numbers is also irrational. So what do you think, true or false? The answer is false. So what is the counter example? How do we show if something is false? We need counter example. What is the counter example? So can you give me an example of two irrational numbers whose product is not irrational, right? Because we have to find an example that has the assumption, not the conclusion. So it has to, the two numbers have to be both irrational, but the product must be not irrational. Not irrational means rational. So take, let's say a equals root 2 is an irrational number. B equals root 2, also an irrational number. So why is root 2 an irrational number? I think you have seen the proof in pre-calculus, but we are going to see it again in this course, hopefully today. Okay, so don't worry, but you already know that root 2 is irrational. B also root 2. Then AB will be equal to root 2 times root 2, which is 2, and 2 is rational. Right? So am I allowed to take both my numbers as root 2? Is that okay? Yes, because the assumption, the question does not say product of two distinct irrational numbers, right? So my counterexample must have the feature that satisfies the assumption, not the conclusion. The assumption is that I have two irrational numbers. It doesn't say that those two irrational numbers must be different from each other, right? So as long as I have two irrational numbers, I can consider that as an example or counterexample. So I'm taking A and B, both of them as root 2. And then the product AB would be root 2 times root 2, which is 2. And 2 is not irrational because it's irrational. Okay. So of course, there are many more examples of this method, direct proof. And you'll see more examples in exercises as well. But for now, let's move on to the next method of proof, which is called proof by contraposition. So next method of proof. So I can call it number 2, proof by contraposition. So we have seen before, that P implies Q, right, is logically equivalent with the contrapositive. What is the contrapositive of P implies Q? Negation Q implies negation P. Right? So P implies Q is logically equivalent with negation Q implies negation P. So what does that mean? That means instead of proving P implies Q, we can prove negation Q implies negation P because these are equivalent with each other. So instead of proving one, you can prove the other. So you could ask me, what is the point of doing that? Because in some cases or some examples, proving the contrapositive negation Q implies negation P is easier than proving the original statement. So it just gives us one more option to prove P implies Q. So instead of proving P implies Q, of course, if you can prove P implies Q using direct proof, feel free to do that. But if it was hard for you to do it, you have also the option to prove negation Q implies negation P, because these two are logically equivalent with each other. So it's logically equivalent with this. So hence, if proving P implies Q with direct proof was impossible or complicated, we could prove negation Q implies negation P instead. And this implies that P implies Q also holds. So let's look at an example. If, so prove if n squared is even, then n is even. Okay, so this is a statement we want to prove that if n squared is even, then n is even. So our first maybe attempt would be using direct proof, right? So let's see whether we can do it with direct proof. So with direct proof, let n squared be even. So if I have an even number, so that means that number can be written of the form, let's say 2k, right? For some integer k. Now, what do I want to have at the end? I want to have n. So that means I have to take square root from both sides. So square root n squared equals square root 2k. Now, how can I know whether square root 2k is odd or even? Because square root 2k, so we can say whether square root 2k is of the form 2k, let's say 2k prime or 2k prime plus 1, right? Square root 2k is not of the form 2k, 2 times integer, or is not of the form 2 times integer plus 1. So that's why we are stuck, basically. So we are stuck. See, compare this with the previous examples that we did. So for example, see when we did here, for example, this one we said n is odd, then n squared is odd, which is similar to what we are doing, but similar to the converse of what we are doing, because here we are assuming n squared is even, then n is even. In the previous example, today we showed that if n is odd, then n squared is odd. So in that example, we said, okay, n is 2k plus 1, then n squared. We wrote it as 4k squared plus 4k plus 1. Then after doing some simple algebra, we could write it as 2 times some integer plus 1. Because there was no square root involved, right? So we could just take a common factor and doing some simple algebra. But here, because I have square root involved, square root 2k, well, I don't know what to do with the square root 2k. I cannot write it as 2 times integer or 2 times integer plus 1. And that's why we're stuck. So we are stuck means what? So we can try different methods. So with direct proof, we would be stuck. But what about with another proof? So we will try. So we now try proof by contraposition. So contraposition means what? See, this is like my P. And then this part is my Q, right? So if P, then Q. Now contraposition would be, we said here, if negation Q, then negation P. So negation Q means what? If Q is n is even. So negation Q means if n is not even, then negation P. Negation P means n squared is not even. So we must prove if n is not even, then n squared is not even. And what's the meaning of this? i.e., if n is odd, then n squared is odd. Right? Not even means odd, right? So when we say we want to show if n is not even, then n squared is not even, means we want to show if n is odd, then n squared is odd. Well, this is exactly the statement that we already proved before, right? So let me repeat the proof quickly. I just showed you, right? So this is the example we did. See? Here. That n be odd, then n squared is odd. So we already proved this, right? So let me just so let n equals 2k plus 1 for some integer k. Then n squared will be 4k squared plus 4k plus 1 equals 2 times 2k squared plus 2k plus 1. So n squared is of the form 2k prime plus 1, and that means n squared is odd as desired. Okay. Well, so this is so hence, if n squared is even, then n is even. All right, so let's look at another example. Prove that if A and B, are positive integers, and if n equals AB, then A is less than equal to root n, or B is less than equal to root n. Okay, so again, one way to do it is try to prove it with a direct proof. But again, if you want to do direct proof, you will be stuck, because you have to start the assumption. Assumption is n equals AB, and then in the conclusion you have root n appear. So then you have to take square root n equals root a times root b. But then how would you make sure that the inequalities appear, or how would you show that a is less than root n or b is less than root n? So you could try, see whether you can make direct proof work or no. But the easier way or better way to do it is to do it with proof by contraposition. So proof by contraposition. So proof by contraposition. So we must prove. Okay, so what should we prove? So see, this is basically, well, a and b are two given positive integers, right? So my assumption here is that if I set n to be AB, then a is less than root n or b is less than root n, which is my q. So we must prove that if negation q, then negation p. So we must prove if. So for two given positive integers a and b. If negation q means if that's not the case that q is true. If that's not the case that a is less than root n or b is less than root n, means what? Means if a is bigger than root n and b is bigger than root n. Do you remember? See, negation of r or s is same as negation r and negation s. De Morgan's law, right? Disjunction, remember, means or, conjunction means and. Negation of r or s is equivalent with negation r and negation s. So negation of a less than root n or b is less than root n is a is bigger than root n and b is bigger than root n. Then, and what is the negation of n equals ab? N is not equal to ab. But now this is very easy to prove. See, a is bigger than root n, so note, so the assumption here is, let's say note, a is bigger than root n and b is bigger than root n. Thus, if I multiply these two together, a times b bigger than root n times root n, and that means ab is bigger than n. Root n times root n is n. So see, if you have two inequalities and everything is positive, you can multiply both sides. If you have two inequalities and of course same direction, right? A is bigger than root n, b is bigger than root n, and everything is positive. Why is everything positive? Well, because root n is positive, not it is not negative, and a and b are bigger than root n, so a number bigger than a positive number is positive, right? So a and b are positive and root n positive. So I can multiply these two. I'll get ab bigger than root n times root n, which means ab bigger than n. And that means what? So if ab is bigger than n, so that means n is not equal to ab, right? Because ab is bigger than n, so that means they are not equal. Well, that's it. So therefore, if n equals ab, then a is less than equal to root n, or b is less than equal to root n. That's what we wanted to show. Okay, so next method of proof. Proof by contradiction. So this is very similar to proof by contraposition. I can say the only difference is that the way that we write and the words and sentences are a little bit different. Just a little bit different, but the concept is almost the same, very similar. So let me explain about this. So see, remember, we want to prove that, if P, then Q. So in proof by contradiction, we assume Q does not hold and we reach a contradiction now this contradiction can be negation P itself, right? And we reach a contradiction which could be negation P, because P and negation P is a contradiction. Recall that P and negation P is a contradiction. Contradiction, if you remember, means a statement which is always false. And P and negation P is always false. For example, it rains today and it does not rain today. That's not possible. That's always false, right? So in the proof by contradiction, we assume Q does not hold. And then we reach a contradiction, which could be negation P. Or it could be a statement contradicting a mathematical fact. For example, 2 equals 0. So once we reach a contradiction, we can conclude that negation Q cannot be true or is not true. And that means Q must be true. Okay, so let me explain one more time. See, we want to show that if P, then Q. We want to prove that Q is right. So in order to show that Q is right, let's assume that Q is not right, which is also what we do in proof by contraposition, because that's why I'm saying that this method is very similar to proof by contraposition. In proof by contraposition, also, we assume Q is not right. We assume negation Q is right. And then we show that negation P is right in proof by contraposition. In proof by contradiction also, we start with negation Q, and then we can either reach negation P, and in that case, it would be exactly what we would do in proof by contraposition, or we can derive another type of contradiction. So if we derive negation P, that would be a contradiction because P and negation P is contradiction. Or we can have another type of contradiction. For example, 2 equals 0. That's also another type of contradiction. So anyways, the summary is that we want to show Q is right. So we assume Q is not right. We reach a contradiction. And this means that negation Q cannot be right, true. So that means Q must be true. And that's exactly what we want to show. So let's look at an example. Okay, so this example, we have already done it, the example was, prove that if n squared is even, then n is even. So solution 1, using proof by contraposition. See above, we already did the proof by contraposition. Now solution 2. proof by contradiction. How can we do it with proof by contradiction? In proof by contradiction, we must assume what we want to show is wrong. We want to show that n is even. So let's assume this is wrong. So suppose that n is not even. So that means n is odd. So that means, n is equal to 2k plus 1 for some integer k. And then this means that n squared is equal to 2k plus 1, the whole squared. And that's 4k squared plus 4k plus 1, which I can write it as 2 times 2k squared plus 2k plus 1. So 2 times some integer plus 1. So that means n squared is odd. And this is contradiction with n squared being even. Please remember in the question, it says that if n squared is even. So we are assuming that n squared is even, but here we concluded that n squared must be odd, and that's impossible. Or a contradiction that n squared is odd and even at the same time. So with contradiction with n squared being even, given as an assumption. So this contradiction shows that n must be even. Okay, and what I want to ask you to do is that please compare solution 2 with solution 1. So you will see that. So solution 1, I mean proof by contraposition, solution 2 proof by contradiction. You will see that both these two solutions are very similar. In both of them, we want to show that n is even. And in both of them, we start by saying that, okay, let's assume n is not even. We start by negation q, in other words. In solution 1 proof by contraposition, we start by negation q and we reach negation p at the end. In proof by contradiction, we also start with negation q and we reach a contradiction. Contradiction could be negation p itself or could be another type of contradiction, for example, 2 equals 0. In this case, the contradiction was negation p again. So that's why in this case, the solutions were basically the same. The core of the solution and the concept of the solution in both cases, both solutions, was that in order to prove the given conditional statement, we proved that if n is odd, then n squared is odd. If n is odd means negation q, and n squared is odd means negation p. Both of them, we did this. But the wording was a little bit different. In proof by contraposition, we said, okay, let's assume negation q, we prove negation p. In proof by contradiction, we say, okay, let's assume q does not hold, which is basically the same as negation q holds. And then we reach a contradiction. And then after we reach the contradiction, we say, okay, this is contradiction with what? And then we say, this contradiction shows that q must be true. And in this case, means n must be even. Okay, now let's look at another standard example of proof by contradiction. Show that root 2 is an irrational number. So proof by contradiction. So again, how do we begin proof by contradiction? By assuming what we want to show is wrong. What do we want to show here? We want to show that root 2 is irrational. So suppose root 2 is not irrational. So what does that mean? So that means root 2 is rational. And if root 2 is rational, how can I write it? I can write it of the form m over n, right? We know that every rational number can be written of the form m over n. So that means root 2 equals m over n for some integers m and n with n not equal to 0. So this is just a definition of a rational number, like we said also today, and you saw in pre-calculus. Every rational number can be written of the form m over n, where m and n are integers and denominator is not equal to 0. Furthermore, we can assume that m and n have no common divisors. Of course, other than plus minus 1. See, any fraction that you consider, so either top and bottom have some common divisors. For example, let's say 2 over 4. So they have common divisors, common divisor which is 2. So, but if there is a common divisor, I can do the cancellation, right? And simplify, and then I'll get 1 over 2, and then 1 over 2 have no common divisors anymore. Of course, other than 1 or minus 1. Or for example, 3 over 5. 3 over 5, already top and bottom have no common divisors and cannot be simplified. So my point is, if the fraction can be simplified, in other words, if there is a common divisor, first simplify. But after simplification, I can get a fraction where top and bottom have no common divisors anymore. So when I said root 2 equals m over n, I'm allowed to assume that m and n have no common divisors. Why? Because if they did, first simplify, and then you get a fraction where cannot be simplified further, meaning that m and n have no common divisors. And that final fraction, you call the numerator m, denominator n. So let me mention here that if m and n had common divisors, divisor or divisors, first simplify. All right. So what do we have now? So we have root 2. So now we have root 2 equals m over n. So if I raise both sides to power 2, I can say 2 is equal to m squared over n squared. And then I can cross multiply. And then I can get 2 means 2 over 1, right? So I can say m squared is equal to 2n squared. Now, m squared is 2 times some number. If a number is of the form 2 times another number, it means that number is even, right? So m squared is 2 times another number. So I can say m squared is even. Now I want to use the previous example that we did here, see? So let me call this example star. In example star, we prove if n squared is even, then n is even. And we provided 2 solutions. So here I have m squared even. So example star above. Example star above implies that m is even. Okay, m is even. M is even means what? So that means m can be written of the form 2k, right? For some integer k, right? If a number is even, means it can be written of the form 2k. And therefore, m squared will be how much? M squared will be 4k squared. All right. Remember, my goal is to reach a contradiction. Now, m squared is 4k squared. I also knew that m squared is 2n squared. So let me call this one 2 star. And let me call this one 3 star. And now I want to substitute. Now substitute 3 star into 2 star. And what do I get? See, m squared is 2n squared and m squared is 4k squared. So that means 4k squared is equal to 2n squared. Now, if I divide both sides by 2, I get n squared equals 2k squared. And that means n squared is even. Again, n squared is 2 times another number, so n squared is even. Again, example star says what? Example star. Let me remind you one more time. If n squared is even, then n is even. Now I know that n squared is even. So that means n is even. So what have we shown so far? We showed that n is even. Previously, we showed that m is even here. See, m is even. We also showed n is even. So we showed that m and n are both even. And this is a contradiction. Why is it contradiction? Contradiction with what? With my assumption that I was assuming that m and n have no common divisors. We established that we're allowed to assume that m and n have no common divisors. But right now I showed that m and n are both even. If m and n are both even, means 2 is a common divisor, right? If you have 2 even numbers, means 2 is a common divisor for those 2 numbers. Number 2 is a common divisor for m and n, but I was assuming that m and n have no common divisors. So this is a contradiction with our assumption that m and n have no common divisors. So this contradiction shows that root 2 is irrational. We wanted to show that root 2 is irrational. We assume that root 2 is rational. We reached a contradiction, and then this contradiction means root 2 must be irrational. Okay, guys, so this is about the methods of proof. Okay, so see you soon next time.